Good morning, friends. Welcome to Water Resources Engineering class. We are dealing with Unit 4, and Unit 4 consists of two parts. One is groundwater hydrology. The second one is water requirement of crops. So we have completed already the groundwater hydrology, and now we are dealing with the water requirements of crops. In the water requirements of crops also, we have completed 3 lectures, right? And we started with the introduction part, then duty delta, that relation, the factors affecting duty delta, those things also we have dealt with actually. And now we are going forward actually to the next lecture, wherein we are studying some of the very important components of this particular topic, water requirements. So this is very crucial in terms of both the theoretical and mathematics problems point of view, right? Let us come. So what we deal today, one we deal is classification of soil water. So last class we have dealt classification of soils. Similarly, quality of irrigation water. These two things we studied independently. Quality of irrigation water and at the same time types of soils. Now what we want to discuss is the classification of this soil water actually. Then what is these relations, soil water relationships and the root zone water actually, which is being utilized for the plant growth. Then what do you understand by the limiting moisture contents and what is the depth and frequency of irrigation, right? Then some of the problems in this. This is the way this lecture is being organized. So let us take it. Classification of soil water. Concentrate on the figure. The water that is present in the soil we may classify under fundamentally 3 heads, right? The water present in the soil can be classified under 3 heads. What are those 3 heads? Hygroscopic water, capillary water, gravitational water. What are the 3? Hygroscopic, capillary, gravitational. Now let us see what is what. So what is gravitational water? For example, if you see, it is only if you see this part of the water. So water present in this zone, that means which is almost very near to the ground level, that which we see. How can I know what is that type of water? If you take a woven dried sample and then allow water to pass through it, the water drains freely through it because of the gravity force. So whatever the soil pores are there, through that the water will flow clearly, and that water which is flowing through the pores of the soil is what we call it as gravitational water. So you need to permit in the irrigation proper drainage. So the gravitational water has to be drained off. That should be first taken. If you don't provide proper drainage, the problem is it leads to waterlogging, which is very dangerous for crop growth. So that's why please remember a proper drainage of gravitational water is needed for any field when you are raising a crop there. If that is not there, it leads to waterlogging actually, stagnation of water. So this stagnation should not occur. It has to flow, it has to be drained actually, and it has very because the soil cannot hold actually. The pressure is very less, so automatically it flows freely. But this water is not available for the plants. So the gravitational water is not available for the plants at all. But what is the use of gravitational water? The gravitational water recharges the groundwater. It reaches to the groundwater actually, right? The water whichever present in the soil, the gravitational water, naturally we need to see that it is drained. properly. So that water is only, we call it as gravitational water. What is it useful for the plant growth? No, it is only helpful for us for recharging the groundwater. So this is the first zone actually. Coming to the next zone, what is capillary water? Because this is the main important zone as far as the plant growth is concerned for you. So this is the water which you utilize for the plant growth. So kindly remember, the capillary water means what? By the capillary action, whatever water is whatever the water that is held in the pores of the soil, because of that surface tension force, water whichever is held in the soil pores, that is what we call it as capillary water. So in this zone, both water is present and air is also present actually. Kindly remember, whereas in this zone it is only freely draining water only, but in this zone air is there and then water is there actually. But how the water is held? Water is held because of the capillary action. So that is what you should remember. The pressure definitely here is more, because to hold that water between the soil particles, the pressure is high, the tension, the force is 1/3 to 31 atmospheres pressure is there. Naturally, the roots can extract the water from the soil pores in this. So that is why this zone is very important, and this is the useful water as far as plants are concerned. The field capacity of a soil corresponds to maximum amount of capillary water the soil can hold after the gravitational water has been drained. Gravitational water has to be drained. The capillary water, how much maximum the soil can hold, that defines the field capacity of the soil actually. Remember, the field capacity of a soil depends on the capillary water which the soil can hold, right? And that is the useful water for the plant growth. Then third one is hygroscopic water. Hygroscopic water in the sense that it is not again for any useful for the crops or from any point of view. The hygroscopic water is not. What do you mean by that hygroscopic water? For example, if you take a oven dried sample, from the oven, if you take a dry sample of soil and then keep it in the atmosphere, then from the atmosphere it absorbs some moisture. Whatever moisture it can absorb, that is what we call it as hygroscopic water. But it cannot be taken out. It cannot be withdrawn actually. No, because if you want to draw that water, the force that is required is so high. It is so high actually. So that's why that plants cannot draw basically that water at all. So that's why it is unavailable for the plants. Right? Please remember, this is the third. So now you tell me, water that is present in the soil can be classified under three headings. One is the gravitational water. Is it useful for the plant? No. What is the use of it? Reaches to the groundwater. The second one is what? Capillary water. It is the water that is held in the soil pores because of the capillary action, because of the surface tension force. Is it useful? Yes. The plant uses that water only actually. The plant roots takes the water from the capillary zone only. The third one is what? The hygroscopic water. What do you mean by hygroscopic water? Keep a oven dry sample actually outside in the atmosphere. Whatever moisture it attracts, that moisture is what we call it as hygroscopic water. Can you draw it? Absolutely no. The pressure required is very, very high actually. So that's why it is not useful at all. So now let us come to the practical definitions. What do you mean by available water? So available water is what finally for us, this is the point actually you should remember. From this point to this point is what we call it as, this is the available water actually. This is the part that is available water. So the maximum limit is what? Field capacity. That means field capacity says what? The maximum water holding capacity is the field capacity. So the upper limit of this capillary water is nothing but basically the field capacity. That means the maximum moisture the soil can hold because of the capillary action. So that is the first thing. So and what is the lower limit actually? That is what we call it as the wilting point. This is what we call it as permanent wilting point, PWP. PWP is the bottom range. So between the field capacity and the permanent wilting point, whatever is there, that zone is what we call it as available water. So out of the capillary water, the whole capillary water is also not available. Out of the capillary water, only the available water is the water that is held by the capillary action, that is maximum thing, that is field capacity minus the permanent wilting point. So that is the second. So that you should remember. What do you mean by permanent wilting point? It is the soil moisture content at which plants permanently wilt. Wilt away means almost plant become dry and plant is dying actually, and it cannot recover even if you pour water actually, because of the lack of water, lack of sufficient quantity of water availability for the roots. The plant is wilting. Wilting means actually it is becoming slowly, the leaves are becoming dry, and slowly, because it slowly, what will happen is even if you pour water also, it cannot really sustain. So it is dying only, the plant is dying. So such state is called as permanent wilting point actually. So kindly please remember, so what this is, the available water, which is very, very important for us for the next discussion. Then what are the soil moisture constants? So soil moisture constants, we can talk about. First thing is saturation capacity. Saturation capacity means what? The maximum moisture holding capacity or total capacity. When all the pores of the soil are completely filled with water, that is what we call it as this. The soil cannot hold any more water by against gravity. Then water held at this stage then includes gravitational water and capillary water, both. That means the water soil sample completely has become saturated. All the pores are being filled with water. That is what we call it as saturation. And what are the two things in that saturation? Gravitational water is there, capillary water is there. Now what we need to do, gravitational water has to be drained out actually. Otherwise, if the gravitational water is kept like that only, the next stage is water logging. So in order to prevent that water logging, then naturally we need to see that the gravitational water is drained and only capillary water remains. Then what is field capacity? First I have taken saturation, that means full, no air at all, completely filled with water. Then next one is field, defined as the amount of water left in the soil after gravitational water has drained away. Once the gravitational water has been drained, so what is the remaining water actually? Only capillary water. That is what we call it as field capacity. Field capacity means we are talking about the available moisture in the soil sample. That is what moisture after the after the gravitational water is drained. Will the gravitational water drained in 2 minutes or 3 minutes or 1 hour? It takes usually time. So allow some time. Before that time it has to be drained. So that's why proper drainage is a must when you are irrigating any land. So if that is not drained, then water becomes stagnant there and the plant will die. Please note that. So usually after 1 or 2 days of saturation, the soil particles contain, or soil pores, soil voids contain both air and capillary water at this stage. This is the upper limit of the available water for the plant. The upper limit of available water for the plants is in the figure, last figure itself I have shown. This is what we call it as field capacity. Right? Soil moisture, then all the remaining. Consider it is ideal moisture condition for the crop growth, because this is one which is really useful for us. Then we told that by capillary action due to surface tension force, the water is held in the pores of the soil. So how to define it? The soil moisture tension is defined as force per unit area that must be exerted in order to extract the water from the soil. The force that has to be exerted in order to extract water from the soil is what we call it as soil moisture tension, because that is one word which is commonly used. Then what do you mean by field capacity definition? It is the weight of the maximum moisture content held in the soil sample, right, divided by weight of the dry soil sample. You take a dry soil sample. So when you take a dry soil sample, allow the water to flow through it. The gravitational water will drain off. Actually, hygroscopic water, anyhow you cannot take it outside. You cannot liberate it outside. So whatever water that is really you can use it is capillary water. So that is what we call it as field capacity, and this is expressed in terms of percentage actually, because when I put it this into 100, if you put it, you get this percentage. So what is the maximum moisture content that is held in the soil sample divided by the weight of the dry soil sample? This is the one. Then what do you mean by permanent wilting point? Because we told that the available water is equal to field capacity minus permanent wilting point. This is what we mentioned. So what that permanent wilting point is? The moisture content at which basically the plants wilt permanently. Wilting is nothing but only drying. Drying finally leads to dying actually, and cannot recover even if placed in a humid chamber. That means even if you pour water now, it cannot recover. Such a stage is reached. Then we say that the plant has reached to a stage of permanent wilting point actually. At this stage, the only water left out is the hygroscopic water and very tightly bound capillary water. Because if you see the zones actually, so it is not just only hygroscopic water, a small quantity of capillary water is also there. So that means, so this is nothing but hygroscopic water plus tightly bound capillary water. That means this capillary water the plant is not able to extract at all. So if suppose the water level, moisture level has come to this level, means after that for the plant there is no water at all, no water available for the plant for the growth. So automatically the plant start wilting and automatically the plant dies also after some time. So that is what you need to understand. So that's why always the moisture level should be above it in order to see that the crop basically is live actually. The plant is not dying, then the moisture content is somewhere in this region. Please don't remember that. Alright. So it is now hygroscopic water plus tightly bound capillary water. That capillary water is not available to the plant. So there is no water for the plant availability for the roots. So naturally automatically the plant will die. So this is what we want to say. Then in this wilting, there are two types of wilting. One is what? Permanent wilting. Otherwise, second one is temporary wilting. So what do you mean by wilting? When the soil moisture decreases, the plants begin to lose its uprightness of the leaves. For example, any plant you just go and observe how the leaves are actually. If the leaves are just upright, the leaves are basically, if you see with your eyes, it is upright and it is having basically turgidity, then naturally they are all live plants actually. For example, if suppose the soil moisture decreases, slowly the plant loses its turgidity and the leaves also almost like rather than straighten in this position, it almost falls down. So that is what we call it as the wilting actually. So because what is the reason for that wilting? The plant roots are not able to extract water from the soil. That is the basic thing. So this condition is called as wilting. What do you mean by temporary wilting? In the case of temporary wilting means, for example, you take any sunny day right? Any plants you see outside in your house also. So on a sunny day, because even though you have now the what soil moisture is there, but the soil moisture quickly can be absorbed, because there it is not only the plant that is taking the water, because of the evaporation, because of the what I call it as the outside temperature, naturally the water is being slowly evaporated, and there are two things coming. One is evaporation is for becoming there, and again transpiration is there. And if suppose the soil moisture is reduced and you don't identify it, normally if you see in the almost because of the high temperature or less humidity or because of the strong winds actually, so that because of that actually what will happen, temporarily it appears for us all the plants are almost just basically almost what I call it as, instead of live and straight position, slowly it is coming down actually. But during the night, naturally, when the moment they attract moisture from the air, and in the night, again they become upright. So that means temporarily they appear as if they are dying, but no. But in the evening again, the moment as the temperature goes down, as the humidity goes high and the winds are less, automatically what will happen? The plant will recover, and then basically it survives. So this is what we call it as temporary wilting. Whereas what do you mean by permanent wilting? Permanent wilting means the soil moisture has fallen to the permanent wilting point zone. So that means if the moisture has come down to such a low level, actually the permanent wilting point, there is no way the plant can recover. The plant will die. That's all what we want to say. So this is the basic difference between the temporary wilting and permanent wilting. Temporary wilting means only because of the temperature, humidity and wind, naturally on a particular day or for a particular period, it appears as if the plant is only drying actually. But by the evening, it absorbs enough moisture and the plant is able to draw the moisture from the roots, and there is soil moisture is there in that. So because of it, it recovers by the evening. So that is temporary thing. If the plant is able to recover, then we call it as temporary wilting. Whereas plant is not able to recover at all, plant dies. That is what we call it as permanent wilting. And what we mean by root zone soil water? The root zone is the depth of soil from which the crop extracts most of its water. Whatever water requirements for the crop is there, all that water requirements is only drawn from the root system. So what that zone will be? Generally, the zone varies from crop to crop. The root zone depth of any particular crop, if you take it, it varies from crop to crop. There are certain crops which are shallow rooted crops, like for example, any onion you take it, wheat you take it, shallow roots only. Whereas if you take it, sugarcane, cotton, they're all deep rooted. But whatever it is, generally the root zone depth for the plants varies from 0.6 to 0.9 for shallow, basically what a rooted plant crops, whereas 1.2 to 1.8 meters for basically for the crops which are deep rooted. And the soil moisture in this zone is critical for plant growth. So again I am classifying the soil moisture. So you all know the soil moisture, whatever the soil water can be classified under hygroscopic water, capillary water and gravitational water. What do you mean by understand? Because these are all small concepts, like what do you understand by limiting moisture content conditions? All this we have studied in the wilting and permanent wilting point also. Again, once again, we are repeating that in a different sense actually. Suppose if the growth of the plant on y-axis, if I take it, and the moisture content of the soil, if I take it, how it looks like is almost like this curve actually. This is the way. What are the things? On x-axis, what you have taken? The moisture content. On y-axis, what you are taking? Rate of growth of the crop actually. So this is how it will be. So the moisture content corresponds to this is what we call it as optimum moisture content. You need to supply that much water only to the plant for the maximum growth. If you supply less or more, that is not useful. Even if you supply more also, plant naturally the growth, if you see, it goes down. If you supply less water, again growth is less. The optimum moisture content is one of the things very, very important for the healthy crop growth. The same thing is being explained to you for in words actually, which you can read. There are two critical limits for this limiting moisture conditions are the soil water availability in the root zone. First one, what I mentioned, the upper limit, always I mentioned it as field capacity. What is the lower limit? I mentioned it as permanent wilting point. So field capacity minus permanent wilting point is what? Available moisture. So this is what number of times I repeated. Again I am repeating actually. Out of this actually 75% approximately is the readily available moisture actually. Then what do you understand by moisture equivalent? Moisture equivalent is nothing but it is again the percentage of water in the soil. The percentage of water the soil can retain against a centrifugal force of 1,000 times the gravity force of gravity. So if suppose moisture equivalent is important for some other reasons actually, right? What that means, what it cannot, even if you apply to the force to that extent, 1,000 times the force of gravity, if you apply to a sample, and then still whatever moisture, whatever the water the soil can retain in the soil mass, that is what we call it as moisture equivalent, and that moisture equivalent should be equal to field capacity. And it is 1.8 to 2 times the permanent wilting point, 2.7 times the hygroscopic coefficient actually. What is the use of this moisture? It provides an index of the soil water holding capacity, and it is helpful in comparing soils for irrigation suitability. You take different soils, if you calculate the moisture equivalent, the suitability of it we can tell. For example, the sandy soils naturally automatically low moisture basically, whereas clay soils high moisture equivalent. Depending upon this low moisture equivalent or high moisture equivalent, we propose actually a particular soil for a particular crop. What do you understand by soil moisture deficiency? Soil moisture deficiency is the amount of water required to bring the soil in the root zone from its existing moisture content to the field capacity. So that means deficiency means what? Optimum, what we always the water should be up to the field capacity, right? The soil, in the soil, the water should be up to the field capacity. Suppose for example, if that there is a deficiency, it is less. So whatever water that is required to bring that water level to the field capacity level, that portion is what we call it as the soil moisture deficiency. So that means you need to add that much water to see that the plant growth is healthy, right? So naturally, then once you are doing, for example, irrigation to water you are applying today, right? Now the automatically evaporation is taking place, transpiration is taking place. Both are taking place actually. So naturally the moisture content in the soil slowly decreases. So again, when you need to again supply, so that how can you know it? This soil moisture deficiency. So what is that soil moisture deficiency? It is field capacity minus the what is the available moisture. It is not permanent. Permanent wilting point means gone case. Only thing is above permanent wilting point, whatever is the available moisture content into D. What do you understand by D? D is the depth of soil which we are taking, and gamma D is nothing but the dry unit weight of the soil actually. If you use this, you can get that. And very, very important actually, what is the depth of water stored in the root zone and what is available to the plants? The available water to the plants, what is the depth of water stored in the root zone of a plant is very, very important. Very simple derivation just to, in order to estimate the depth of water stored in the root zone of a soil, containing water up to what level? Field capacity. Let D be the depth of root zone first. What is D? D is nothing but the depth of the root zone, and FC is the field capacity. Second one, right? Let gamma D is the dry unit weight of the soil. Gamma D is the dry unit weight of the soil. Gamma W is the unit weight of water, right? Consider only 1 square meter of soil. 1 square meter actually. 1 square meter means if you take it, this is the 1 square meter, 1 meter actually. Now the soil depth, if you take it actually, so this is the depth of the soil, you put it. So this depth is nothing but you have put it as D, right? Water, now weight of water retained in unit area. How much water you can retain in this unit area? How much water, gravitational water is drained off, hygroscopic water is not there. So field capacity, that is first thing. And when I take field capacity, what is the dry unit weight of soil, and into area is depth is basically D, and this is D into 1. This will give you volume, right? D is the depth, into 1 will give you the volume, into gamma D will give you actually the weight, into FC will give you exactly weight of water retained in the soil. So this is the first thing. So start from here. First, what is the volume of the soil? The volume of the soil is D into 1 into gamma D. So that will give you weight of the soil. And what is the weight of water in the soil? The field capacity. So this is first thing, right? When once you got the weight of water stored in the stored in the root zone in a 1 square meter area, right? So if you want depth, then what you will do it actually? So if already you have found out basically this, divided by what is the unit weight of water. So I put that actually. So I got depth of water stored in the root zone. Depth of water stored in the root zone also can be calculated. So depth of water can also be calculated. What is gamma W into depth of root zone? Depth of root zone. So this and this, if I equate, what is depth of root zone is equal to this divided by this. That is what exactly I have put here. So how you are deriving the formula? First, weight of water retained in the soil. How you get the weight of water retained in the soil? What is the volume of basically the entire, or what you call it as entire root zone, basically 1 square meter area into D is the depth of soil. Then right, into gamma D, if you put it what? Weight of the soil. And in that, what is the moisture that is there? Up to field capacity. So what is the weight of water retained in the soil? Into field capacity, you get it. So that is one part. What is the second part? What is the depth of water stored in the root zone? I want to calculate. So now again I want to calculate what is the weight of water stored in the root zone. That is nothing but actually the unit weight of water into depth of water stored in the root zone. That I put it. I equated both the things. When I equated both the things, this is the equation actually. Out of this, this depth of water stored in the root zone is what I call it as dW, right? Now this is nothing but if I take it, it is gamma D by gamma W. This is also one thing. And D is I have taken depth of soil, actually soil sample, and FC is the field capacity. So directly I have written here full field capacity. But full field capacity, is it available? Minus what I need to show? The wilting point actually. So that is what I have shown. So this is the next thing actually. So finally, and this gamma D by gamma W is nothing but what? The weight of dry sample divided by basically weight of water, unit weight of water. So what it represents? Specific gravity. So that's why I have written it as specific gravity. So finally, what is the available moisture depth actually? What is the depth of water present in the root zone? So naturally it is nothing but actually the specific gravity, that is nothing but gamma D by gamma W into depth of soil into field capacity minus wilting coefficient. So depth and frequency of irrigation. So that means, what do you mean by that actually? Frequency, how many number of times you need to water to raise a crop properly. Because it's not just once you do it today and keep quiet and you get the crop, that is not the way. No? So how many times you need to really water the crop? How many times you need to send the water to the crop? Every day also you don't need to send. Depending on the requirements, you will be sending it. So depending upon the soil moisture, you will be giving the watering to the plants actually. So that is what I mean by depth and frequency of the interval between two consecutive irrigations. Consecutive irrigation means today I have given water to the plant. After how many days again I give the water to the plant. So this is the interval, the period actually. Period between two waterings. Again we may give water. This is again. So that is what I mean by frequency of watering actually. So it depends on rate of water used by the crop. That is what we call it as nothing but the consumptive use, or the what I call it as evapotranspiration. And what is the available soil water? That is nothing but field capacity to wilting point. So these are the two factors. So that's why the frequency of irrigation watering is equal to two things are there. One is the moisture, available moisture depth in the root zone, that is dW, divided by what is the utilization, that is consumptive use. So excellent bit actually. So kindly remember the frequency of irrigation, or the time period between interval between two consecutive irrigations. It is nothing but one is the depth of the root zone or depth of available moisture divided by basically the consumptive use. This is one of the important points actually. So I will stop here.
Like, share and subscribe. Hit the bell icon for more updates.